Let's consider a simple common source amplifier where we drive it with some ideal current source I naught. And let's say that our input signal is some voltage V bias with an AC component of Vn of T. And we take our output voltage at this pin as per usual. So this is our drain, our gate, and our source. So what we should expect to see is that our overall output voltage will be what I'm going to call VODC, representing the large signal bias voltage at the drain, plus the small signal component, which is just going to be, so let's call this the out of T. Okay, so for our common source amplifier, our small signal voltage output is going to be negative GM times R out times Vn of T here, where it's different slightly from what we saw when we reviewed the common source amplifier, because instead of loading this guy with some resistance RD, instead we're loading it with an ideal current source, which has an infinitely large internal resistance. So this term right here, GMR out, is what's called the intrinsic gain of our amplifier circuit. Okay. It's called the intrinsic gain because it represents the largest possible voltage gain achievable by this single transistor circuit, right? So if we bias this guy with a resistor instead of a ideal current source, we would see that the gain of our circuit actually gets smaller because that resistance RD would be in parallel with the internal resistance of the the small signal internal resistance of the MOSFET R out, right? So if we want to achieve a higher gain than what is capable with this amplifier, we have a couple of different options. And that's what we are going to explore today. Okay, so to achieve a larger voltage gain, or just as a refresher, that's going to be the small signal voltage V out divided by the small signal voltage V in. We have multiple options. The first one that I want us to consider would be cascaded amplifiers. So when we're cascading amplifiers, this is going to be similar to what we did way back in circuits 2 with op amps, where we just chained multiple amplifiers together and observed that the gain of the whole system was the gain of the first stage multiplied by the gain of the second stage and all that kind of good stuff. So with a cascade of common source amplifiers, this would look something like this. So we would have two common source amplifiers. Like so. And what we're going to do is we're going to apply our input signal here. So again, this will be V bias plus Vn of t. Here, we will have our overall output voltage. So VODC plus V out of t. And we chain these guys together by taking the output voltage from transistor M1 and applying it at the input of transistor M2. Now, I'm not going to worry about the fact that transistor M1 is going to have a DC offset component of its output voltage here. So I'm just going to worry about what this small signal output voltage, which we'll call V out 1 of t is. So we could say that V out 1 of t should be what? Yeah, negative GM1 R out 1 Vn of t, and the AC portion of our overall output voltage, V out of t, will then be negative GM2 R out 2 times V out 1 of t, which looks like GM1 R out 1 times GM2 R out 2. And I'm running out of room here, I apologize. Close this menu. I need to save this and restart, or it's going to keep making that terrifying noise. So if transistor M1 and M2 are identical, then we would see that our AC output voltage, or our amplification, actually, our amplification would be GM times R out squared. Right? So when we cascade these two amplifiers together, it's just the product of the gain stages, which is exactly what we would expect. All right. Nothing particularly wild or crazy about this, but it is arguably an inefficient method by which to boost the gain. So I say that because what's the DC power draw of this system as compared to the last system, right? So if we look up here, what's the DC power consumed? So power is voltage? I disagree pretty wholeheartedly. Yeah, that's it. VDD times our reference current of I naught. That's the total voltage drop over the system multiplied by the total current flowing through the system. So for this guy right here, our DC power is going to be what? Well, it's two of them, so it's twice VDD times I naught, right? Now, for some applications, drawing twice as much power as a single stage might not be a big deal, but for other applications, it can absolutely be a problem. So what we are going to do now is figure out how we can get a similar voltage gain while lowering the amount of DC power consumed to achieve it. So let's do this on another page. I thought I turned you off. So our second option is going to be the cascoded amplifier. So in our last class, we cascoded transistors and found out that the overall output resistance of that combination was greatly increased than what was able to achieve by using a single transistor, right? So as a quick reminder, our cascode, something like this, where we have two transistors stacked on top of each other. I'm going to put M1 on the bottom, M2 on the top, and we observe that our output resistance, R out, was GM2 times R out 2 multiplied by R out 1. So we wound up scaling the output resistance of transistor M1 by a factor of GM2 times R out 2. So effectively that transistor M1 amplifies, or another way to think about this, the output resistance of transistor M1 is amplified by the intrinsic gain of transistor M2, okay? So to make an amplifier that utilizes this cascoding technique, we would have something like this. Here's I out, and then we're going to have those stacked transistors. Like so. This is going to be transistor M2. This is transistor M1. We are going to apply only a bias voltage. So let's call this B bias 2 to transistor M2. And we are going to apply a bias voltage and a signal voltage to transistor M1. And we will see at our output some voltage VO DC plus V out. So we know that the output resistance seen looking down here is GM2 times R out 2 times R out 1. So instead of going into a very involved calculation for what our gain is and all that kind of stuff, we're going to approach this qualitatively rather than quantitatively like we did back in electronic circuits 2. So I'm going to ask what I hope are a couple of simple questions. We shall see. What is the small signal current that flows through transistor M1? So let's start with what I hope to be a pretty basic question, I guess more basic than that one. What does a transistor do, right? A transistor can do one of two things. It either acts as a switch or it acts as a voltage controlled current source, right? So the small signal drain current should simply be the transconductance of transistor M1 multiplied by that input voltage Vn. Because this guy's job is literally to convert that input voltage into a drain current. That seem reasonable? Okay. Let's call this guy ID1 and this guy here ID2, since ID1 flows through transistor M1 and ID2 will flow through the transistor M2. So what's ID2? It's literally the exact same current. All right. So from this, we can say that our output voltage as a function of time is just going to be our current GM1 times R out 1. Hold on, I think I'm making a dumb mistake here. Yep, totally making a dumb mistake. That should not be R out, that should be B in. Multiplied by the output resistance this small signal current sees. All right, so we know the current, we know the resistance, we know the relationship between the input and output voltages includes a negative sign because our common source amplifier here, which is what this guy at the bottom is, gives us a negative gain. And so what we wind up having there is negative GM1 times GM2 R out 2 times R out 1 times Vn of t. And therefore, our small signal voltage gain for our system is negative GM1 R out 1 GM2 R out 2, or negative GM squared, or negative GM times R out, and I'll just square the whole thing. If M1 is identical to M2, right? So I believe that that analysis is probably much more straightforward than what we did in 336. All right, so what is the total DC power consumption of this guy? So what's the total voltage drop over the system? From VDD to 0, right? The current flowing through it is I naught, so it's just VDD times I naught. All right, so by cascading things here, we have seen that we get the same gain multiplied by a factor of -1 as we got by cascading our transistors together, while only consuming the same amount of DC power as our original single stage amplifier, okay? Now there's a third option here, and it takes a little bit of explanation to do, and you will probably ask yourself why the hell we're doing it by the time I get done with it. And the short answer is it works great for very specific types of op amps, which is why I'm going to talk about it, okay? So actually, let's slow down a bit though. I forgot something pretty important here, right? For us to get this voltage gain, we are making an assumption. And that assumption is that transistor M1 is operating in the saturation region and that transistor M2 is operating in the saturation region, right? So we should probably figure out what the constraints on our bias voltages are to make this guy behave correctly. I think that's a pretty reasonable thing to do, right? So what I'm going to do real quick is identify this nodal voltage here, VD1, because it's going to play a very important role in how we figure things out, okay? So we know that that reference current of I naught is going to flow through both of these transistors, right? So we know that V bias 1 is effectively going to come about from our overdrive voltage, or effectively the feedback that we talked about last class, right? So if that transistor M1 is carrying a current of I naught, then that bias voltage, V bias 1, will settle to what it needs to be to make this guy work. Okay, so we're going to focus our analysis on what's going on for V bias 2. So V bias 2 is going to be that voltage that I've identified, VD1, plus the gate source voltage across transistor M2, VGS2. Recall that this guy specifically is evaluated at that current I naught, right? So the minimum value that we could apply here really depends on what happens as we lower that quantity V bias 2, right? So VGS2 is a fixed value because there's a certain amount of current that's flowing through this, there's a certain amount of DC current flowing through this transistor because that reference current I naught forces that to happen, right? So as V bias 2 gets smaller, what happens to that voltage VD1? It gets smaller. It has to, right? Because they're related by a constant factor, okay? So if we biased that voltage V bias 2 at a low enough value, what's going to happen is that VD1 can get so low that transistor M1 enters the triode region. Does that make sense? Right? So as we push V bias 2 down, VD1 gets pushed down. And if VD1 ever becomes less than, what would it be? I guess VD sat 1, then our transistor enters the triode region. So from that, we can say that VD sat, excuse me, VG2, V bias 2 minimum would be VD sat 1, which is the minimum voltage required to keep transistor M1 in saturation, plus VGS2 evaluated at I naught, which is going to look like the square root of twice I naught divided by mu n C ox W over L1. I'm just doing this generically in case our transistors are not of the same size, plus VTH of M2 plus the square root of twice I naught over mu n C ox W over L2. And I've indicated V8 or VTH2 here because since the source of transistor M2 isn't at ground, body effects may make this guy slightly larger than what we would see for the threshold voltage for transistor M1, right? So arguably this thing is going to be pretty dang close because body effects is usually about 1/10 the size of the transconductance effect. So it's going to be pretty small, but it might be a little bit larger. Now, if we bias this guy with a resistor instead of a current source, we could also have a similar but opposite problem, right? If we had a resistor here instead, we could see that if we increased the value of V bias 2, there might become a point where transistor M2 is no longer in saturation due to the DC output level of the system as a whole, right? So that means that we're going to have a V bias 2 max of VTH2 plus VODC. Let me make sure that's what I called it. Yeah, VODC. So in practice, we need to keep that voltage V bias 2 somewhere between these guys to keep both transistors operating in saturation so that we get the large output resistance, which translates into us having a large gain for our system. Okay. So our third option, or do I need to stay on that page for a minute for people to write stuff down? Okay. So our third option comes from looking at our regular cascode. All right. I'm not going to give this guy a name just yet. So if we look at this guy, or if we look at our regular cascode, where we have some current I naught, here's transistor M2, here's transistor M1. Here is our output voltage, VODC plus V out as a function of time. What type of amplifier do we see here on the bottom? So let's treat this as if the output voltage for transistor M1 serves as the input voltage for transistor M2. We could treat this cascoding thing as a cascaded amplifier as well, in a sense. So what kind of amplifier is formed by transistor M1? So it's common source, right? Our input signal, our small signal input is applied to the gate. The source is our common terminal because it's held at ground, and our output is taken at the drain of transistor M1. So this is a common source amplifier. What kind of amplifier is transistor M2? So the input is applied at the source, the output is taken at the drain, and to small signal, that V bias 2 is now ground. So this is a common gate amplifier. So we can say that our original cascode is the sum of a common source amplifier and a common gate amplifier. And to this point, we realized this common source stage with an NMOS transistor, and we realized this common gate stage also with an NMOS transistor. Now, what is interesting is that the small signal model of a PMOS transistor and the small signal model of the NMOS transistor are literally identical. So we could replace either of these stages with a PMOS transistor, and we would actually wind up getting the exact same result. Okay. So when we replace the common gate stage with a PMOS transistor or a common gate, a PMOS common gate amplifier, what we wind up getting is what's called the folded cascode amplifier. So what that's going to look like is this guy. We're going to have some current I1. And over here we have V bias 1 plus Vn of t. And over here on the right-hand side, we're going to have a PMOS transistor. So notice that the arrow is flowing in. So that's how we know it's a PMOS. And I'm drawing it this way because for a PMOS transistor, typically speaking, the source is at a higher potential than the drain. And so I'm just drawing this to reflect that. We bias our PMOS transistor with a second current source, which I'm going to call I2. And then we take our output here. Like so. So if we looked in here for our output resistance, small signal output resistance, what would we see, right? So both of our DC current sources become open circuits. And so we literally just see two transistors with identical small signal models stacked on top of each other, which is exactly what we saw for our regular cascode. So it stands to reason then, if this is transistor M1 and this is transistor M2, that our output resistance will still be GM2 times R out 2 times R out 1, where now we can pretty much definitely say that the transconductance of transistor M1 and M2 are different, and the output resistance of transistors M1 and M2 are different, right? With regards to biasing, we know that transistor M2 must be drawing a current of I2 from its source to its drain. And so what can we say about the current that the DC current that transistor M1 is drawing? Exactly right, I1 minus I2, good old Kirchhoff's current law. All right. What about our small signal current? Same as what? Small signal current means that those current sources are open circuits, right?
My current going.
What does transistor M1 do? Converts that input voltage into a current. Yeah. So GM1 Vn of t. So this current right here must be GM1 Vn of t. So we still have that current of GM1 times Vn of t flowing through this output resistance. So we observe then that our voltage gain for this system, AV, is just negative GM1 R out 1 times GM2 . There absolutely are constraints as to what this voltage V bias 2 can be. And it will be one of your 2 homework problems to figure that out. All right. So these folded cascode amplifiers are interesting because we wind up getting more headroom out of them because of effectively where in the signal path we're taking the output voltage, right? And it's still the drain of transistor M2, but because of the way a PMOS circuit operates, this drain is going to be at a significantly lower voltage than it was in our telescopic cascode amplifier, right? So we wind up getting more headroom, but we'll find that these folded cascode amplifiers are used very widely in what are called operational transconductance amplifiers, okay? So the telescopic cascode, which is what we are familiar with, is used in conventional op amps, and folded cascodes are used in transconductance op amps. So these guys do better for driving capacitive loads, and telescopics do better for driving resistive loads. That's their fundamental difference. I have 3 pages of notes written on differential amplifiers, but I'm thinking about stopping here for today because I wanted to ask you guys a question. So we are getting fairly close to designing our op amp here. Actually, really, once we get through a differential amplifier, it's not going to be too much longer before we have a single stage op amp and all that kind of good stuff. But what can inform some of the choices that we make in op amp design are considerations for the noise in the system. So my question to you guys is, do you want to just plow ahead and say, let's ignore what contributions noise has? Or do you want to spend a day or 2 learning about the noise constraints? Let's learn about the noise. Okay. So I have exactly 0 notes made about the noise to this point. So I will be spending my weekend making up those notes. So we're wrapping up about 20 minutes early, which I'm sure you guys don't mind because it's Friday. So, all right. The test, exam 1 is due today, technically, right? Is that right? Yeah. So if you haven't finished that, what the heck have you been doing for the last 2 weeks? Please get it in the next 3.5 hours.